Today we're going to continue looking at section 5.2, which is right triangle trig. We specifically today are going to recognize and use fundamental identities, and we're going to use equal cofunctions of complements. So a fundamental identity, it says many relationships exist among the 6 trig functions. These relationships are described using trig identities. All right, these first 6 identities should look familiar. We talked about these reciprocal identities when we first introduced to you the 3 new trig functions of cosecant, secant, and cotangent. Now, if you have your flip book, you want to open up to the very first flap there, and at the top left, you'll see where it says reciprocal identities and 6 empty boxes. You are going to then fill out those boxes with these 6 identities, right? The flip book is then for us to use as a guide where we have everything together with all of these different identities. So remember, sine and cosecant relate to each other, cosine and secant do, tangent and cotangent. So pause the video if you're not done writing, and then unpause to move on. The next set of identities we have are quotient identities. Remember, quotient means division. So it makes sense that we have 2 things here that are being divided. You'll find this in your flip book on the same thing as with the reciprocals. It's just right below it. So tangent of theta is sine over cosine, and cotangent is cosine divided by sine. Now, as long as you know that tangent is sine over cosine, you don't necessarily have to memorize cotangent by heart because remember, cotangent and tangent are reciprocals. So that's why we just flipped around the sine and the cosine. Next, you'll have to go to the flap that says Pythagorean identities. We've got 3 of them, so fill them out at the top. We've got sine squared of theta plus cosine squared of theta equals 1. We have 1 plus tangent squared of theta equals secant squared of theta. And we have 1 plus cotangent squared of theta equals cosecant squared of theta. Now, you are going to need to have these identities memorized, but with the Pythagorean identities, I actually only have 1 of them memorized. The only one that I have memorized is this first one, that's sine squared plus cosine squared equals 1. The reason for that is I can actually manipulate that and turn it into the other 2. And that's why I don't have them memorized. But I do need to know the quotient and the reciprocal identities in order to make that possible. So if you look underneath where it says examples, I want to focus on the middle one. 1 plus tangent squared of theta equals secant squared of theta. Okay, so in the example box, I'm going to write sine squared of theta plus cosine squared of theta equals 1. And I'm going to show you how I can manipulate it to look like 1 plus tangent squared of theta equals secant squared of theta. To do that, I am going to divide every single thing in this equation by the cosine squared of theta. So by dividing by the cosine squared of theta, this very first ratio right here is actually dealing with our quotient identity. If you remember, sine divided by cosine is tangent. Now, the only difference is that these are squared. So that's why sine squared divided by cosine squared, that's actually going to turn into tangent squared of theta. We'll bring down that addition sign. Notice that cosine squared divided by cosine squared is 1. And if I look at this very last fraction, well, that is a reciprocal. Notice that the reciprocal of cosine is secant. So hopefully it makes sense that the reciprocal of cosine squared is going to be secant squared. So yes, the tangent squared and the 1 are flipped around, but it is the exact same identity. So then that's going to be the same kind of thought process we do for the last one here. So once again, in the example at the last box there, let's once again write sine squared of theta plus cosine squared of theta equals 1. And I'll show you how we can manipulate this to look like that last example. This time, we are going to divide every single thing by the sine squared of theta. Okay, notice that sine squared divided by sine squared is 1. Bring down that addition sign. If we take a look at the second fraction, that's actually a quotient identity. Cosine divided by sine is cotangent. With both of them being squared, it turns into cotangent squared of theta. And this last fraction here, that is another reciprocal. The reciprocal of sine is cosecant. So the reciprocal of sine squared is cosecant squared. So notice how, once again, as long as I know that first Pythagorean identity, either divide by the cosine squared for every single thing or divide by the sine squared, and you'll get the other two Pythagorean identities. The only other thing that I want to look at with this first highlighted Pythagorean identity is in the example box. We can technically manipulate this equation. So if I was to deciding that I want to get the sine squared of theta by itself, I could do that. In an equation, I can move something from one side to the other by doing the opposite. So to move that cosine squared, I would have to subtract. So 1 minus the cosine squared of theta is sine squared of theta. So that is a Pythagorean identity. It's just taking what I have highlighted and manipulating it. So the same idea holds true. If I wanted to get the cosine squared of theta by itself, that means the sine squared had to move to the other side by, once again, being subtracted. So cosine squared of theta is the same thing as 1 minus sine squared of theta. All right. So let's use those identities and let's look at this example. It says use a trig identity to find the cosine of theta given that the sine of theta equals 11 over 61. Okay, so if it's asking for us to use a trig identity, we've talked about 3 of them. We've talked about reciprocals. We've talked about quotients. And we've talked about Pythagorean identities. So in this problem, I'm giving a sine. If that's the only trig function I'm giving us, and I want to figure out how to get to cosine, let's think about this for a second. So my first question is, are sine and cosine reciprocals? Because if they are, we're using the reciprocal identities. But hopefully you're all yelling at the computer, no, they're not. Because sine and cosine are not reciprocals, it doesn't make sense to use reciprocal identities. If I look at quotients, so the quotient identity, it does involve sine and cosine, but if you remember, sine divided by cosine equals something, it equals tangent, or cosine divided by sine equals cotangent. Because I don't have tangent or cotangent, and I'm only given sine, it doesn't make sense to use the quotient identities. So that leaves us with the Pythagorean identity. And so once again, if we go to the Pythagorean identity, there is one that deals with just sine and cosine. That was that sine squared of theta plus cosine squared of theta equals 1. And so because I know what sine is, I can plug that in to the sine squared term. I just have to be careful. Since this is being squared, I'm going to take the ratio that represents sine, which is 11 over 61, and I have to square it. We still have plus the cosine squared of theta, and this still equals 1. So let's go ahead and do our algebra, and we can figure out what cosine is. So to square a fraction, I square the top. So 11 squared is 121, and I square the bottom to get 3,721. Because the right-hand side is a number 1, I'm going to turn it into a fraction with the same denominator of 3,721. That just means the numerator has to be the same thing. Why did I do that? Well, I want to get the cosine squared by itself. So I'm going to take the 121 over 3,721, and to move it to the other side means I have to subtract it. So this gives me the cosine squared of theta by itself. Because I have the same denominator, I get to keep that denominator, and now I'm going to subtract the numerators. Well, that subtracts into 3,600. I'm not quite done because I want the cosine. Right now I have cosine squared. So that means that I'm going to take the square root of both sides. Well, when you take the square root of a fraction, you can break it up as the square root of the numerator divided by the square root of the denominator. Okay, so that gets us the cosine by itself. But now here, hopefully we're okay that the denominator actually is going to go back to being 61. Because how did we get the 3,721? We squared 61. Okay, if you take the square root of 3,600, you get 60. So this would be our final answer. Let's take a look at another example. It says use identities to find tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. When necessary, we are going to rationalize the denominator. Notice this time they're giving us two different trig functions. And when it says to use identities, that means you can use more than one. So once again, we have reciprocal identities, we have the quotient identities, and we have the Pythagorean identities. So we can essentially use all of them, but you probably want to make your life a little bit more easy. So let's try to figure out what the easiest identities are to use in order to get to my answers. So let's just go down the order that's listed. Let's start with tangent. So because I'm given sine and cosine, well, tangent isn't the reciprocal of either sine or cosine. So the reciprocal identity isn't going to work in this particular case. But if you think about the quotient identity, remember tangent is sine of theta divided by cosine of theta. Because I have both sine and cosine, I can plug those ratios into this problem. So 2/3 go on the top, square root of 5/3 goes in the denominator. Because we're dividing by a fraction, I can keep the numerator, change division to multiplication, and I can multiply by the reciprocal. Now, because there's a 3 on the top and the 3 on the bottom, that goes away, and it leaves you with 2 divided by the square root of 5, which to finish it out, we have to rationalize. So I'll multiply the top and the bottom by the square root of 5 to give me 2 root 5/5. And there is my first answer. Moving on, we can look at the cosecant of theta. Remember, if I'm thinking about reciprocals, quotient, and Pythagorean, I want to figure out which one's the easiest or fastest one based off the given information. And now we not only have sine and cosine, but we also have tangent. So we have more information to go off of. Hopefully you're recognizing that cosecant, the fastest one, would be probably the reciprocal identity. Remember, that's 1 divided by the sine, okay? It's the reciprocal of sine. And so in this case, because sine is 2/3, all I have to do is flip it around. 3/2 would give me my reciprocal for cosecant. Moving on to secant of theta. Once again, what's the fastest way to get there? Well, probably understanding that its reciprocal is 1/cosine of theta. That might be the fastest. Just like the cosecant, I can just take my cosine and flip it around. That gives me 3 over the square root of 5. And then just like the tangent, we're going to have to rationalize. So I multiply the top and the bottom, and that gives me 3 root 5 on the top and 5 in my denominator. And there's my ratio. Moving on to the last one, cotangent of theta. This one you probably have the most options because now that you have every trig ratio except for that, honestly, you can use any of the reciprocals, the quotients, or the Pythagorean identity. So it's just a matter of which one's probably the fastest. Once again, probably the fastest is going to be the reciprocal. So because tangent is 2 root 5/5, well, if I flip it around, the radical would be in the denominator and I'd have to rationalize. So once again, going back to the ratio prior to rationalizing it is going to make your life so much easier when you do your reciprocal. So flip 2 over square root of 5 around and square root of 5/2 would end up being that final answer. All right, moving on. Trig functions and complements. So if you remember from geometry last year, two positive angles are complementary if their sum is 90 degrees, but now we can even relate it to radians this year. So it's also two angles that add to pi over 2. So sketch this picture right here. We're going to use this triangle ABC, where notice one angle is theta and one is 90 degrees minus theta. And using this triangle, we're going to compare sine of theta and the cosine of 90 degrees minus theta. So we're thinking about SOHCAHTOA here because I want to create ratios. If I want the sine of theta, we're looking at, obviously, the angle theta. What is opposite? Well, that's what's across. A is what's across from that theta. The hypotenuse is what's across from the 90. That's C. So A over C is the sine of theta. Now I want the cosine of 90 degrees minus theta, which means I'm looking at the angle up here at the top. Cosine is adjacent over hypotenuse. Well, adjacent is the leg that's right next to it. That would be A. The hypotenuse hasn't changed. That's C. So if you notice, this is not a coincidence. Those ratios are the same. That's because the sine of theta will always equal the cosine of 90 degrees minus theta. I just proved to you this new identity, which is called a cofunction. So if you, and I keep messing this up, that should be, okay, so essentially then cofunctions are going to be where you're taking two of the angles in your triangle, and remember, they're complementary of each other. So f of theta equals g of 90 degrees minus theta, or g of theta equals f of 90 degrees minus theta. These are cofunctions. So in your flip book, go to the first flip again, and the last 6 boxes there where it says cofunction identities, you can write these 6 things. Notice that it says that theta, if it's in radians, you get to replace all those 90 degrees with pi over 2. But essentially with our cofunctions, like I said, we just proved that sine and cosine relate to each other. Well, tangent and cotangent relate to each other with cofunctions. And then the reciprocals of sine and cosine, which is secant and cosecant, those relate to each other as well. So pause the video if you're not done writing, and then you can unpause to keep going. So let's use that information of cofunctions, and let's find the same value as the given expression. So here I'm giving a sine of 46 degrees. So remember, what relates to sine when we're talking about a cofunction? Well, that would be cosine. But the angle that I want isn't 46, it's the complement. So it would be 90 degrees minus 46 degrees. Well, 90 minus 46 is going to give us a 44 degree angle. So the cosine of 44 degrees is the same thing as the sine of 46 degrees. And you can prove that to yourself by putting it into your calculator. If you type sine 46 and hit enter, you are going to get the decimal of 0.71933998. If you then do the cosine of 44, you will also get 0.71933998. They are identical because of this idea of cofunctions. So let's look at another example, this time in radians. We're dealing with cotangent. So when we're talking cofunctions, tangent relates to that. But remember, pi over 12 is not the angle that I want. I want the complement. So remember, I can replace 90 with pi over 2 for radians, and I want to take pi over 2 minus the angle that is given, which is pi over 12. Now, because these don't have the same denominator, I'm going to find a common denominator. That common denominator would be 12. So that means multiply the top and the bottom of that first fraction by 6, and we will now end up with tangents of 6 pi over 12 minus pi over 12. Well, now that you have the same denominator, you get to keep that denominator and you get to subtract the numerator. 6 pi minus pi would be 5 pi. I put them in the parentheses. You don't necessarily have to have it in parentheses, but this would be then my cofunction. Once again, you could prove it to yourself by putting that into your calculator and seeing that you get the same answer. Be aware that you would have to have your calculator in radian mode, and technically, if you want to put this into your calculator, you would have to do 1 divided by the tangent of then pi divided by 12. Like that's how you would have to put it in to verify. But you don't have to. I'm just letting you know that if you do want to, for whatever reason, check, you can. All right, so pause the video and see if you can try these 2 checkpoint problems. Okay, so for the first one, finding a trig identity, if you're only given one trig function like that, secant and tangent relate to each other through the Pythagorean identity. So kind of like our first example, if 1 plus tangent squared of theta equals secant squared of theta, I plugged in the number for tangent, made sure I squared it. In this case, because all the numbers are on the same side, I just had to combine them. So you can think of 1 as like 81 over 81. And then when you took the square root to get secant by itself, you get 41 over 9. In the second example, remember cosine and sine relate to each other. Because we're in radians, I had to find a common denominator, which would be 6 because I multiplied the top and the bottom by 3. And then when I subtract, I get negative 2 pi over 6. So you can simplify that down to negative pi over 3 for your radian value.